Alrighty, so we can move horizontally now. Let's work on our vertical movement. You'll see that we already are invoking the move vertically method, which is where we're going to handle pretty much all of our vertical movement code. So in this video, we're going to implement that method in addition to putting together our gravity and our jump. All right, so move vertically is currently empty. What is it going to contain? Well, it's pretty much going to contain a very similar implementation to our move horizontally method. In fact, most of it is the same. There are only a small, there's very few differences between the two, mostly having to do with slopes. So let's go ahead and do that. Move vertically, what do we do? First thing we want to do is say var is going up. That is not how you spell is going up. Is going up equals delta movement dot y is greater than 0. So just like our is going right method up here, we check to see, or whoops, delta movement y is greater than 0. We check to see if we're going up or if we're going down. Next up, ray distance. What is our ray distance going to default to? Well, just like before, our ray distance is going to effectively be mathfabs delta movement y plus skin width. So that's how far our ray is going to be shot out, and our ray will either be shot out above us or below us. Next up, ray direction. Yeah, speaking of if it's going to be shot up above or below, we need our direction. Our direction is going to be, if we're going up, we want to do vector2.up, which is a unit vector in the up direction. Otherwise, we want to negate vector2.up, which is the same thing as vector2.down, which doesn't exist for whatever reasons. Next up, let's calculate our ray origin. Remember, our ray origin is where we're going to start shooting our rays. And what we're going to do is we'll say, if we're going up, then we want to raycast top left. Otherwise, we want to raycast bottom left. So that just determines where we start shooting our rays, top left or bottom left. Okay, next up, what we're going to do is we're going to say ray origin dot x plus equals delta movement dot x. So we're actually going to be shooting our rays on it as an offset to where we're trying to go in the x direction. Now we can do this because we've already calculated the x movement. See, we've already done move horizontally. Therefore, rayOrigin.x will give us the position that we are trying to go to as opposed to the position that we are currently at. Alrighty, next up, let's go ahead and say var standing on distance equals float.maxValue. We'll talk about that here in a moment. Okay, so that pretty much looks like our move horizontally method with a couple modifications. Now we're going to enter our loop, and our loop is going to be pretty similar to our move horizontally. For I equals 0, I smaller than total vertical rays, I++. Now we have to calculate our ray vector. Whoops, I smaller than total vertical rays is going, wow, there we go. I equals 0, I smaller than total vertical rays, I++. Next up, we calculate our ray vector. Our ray vector will be a new vector2, passing in the origin of our ray, x, plus I times horizontal distance between rays, comma, ray origin y. That's because, as with our move horizontally, we were moving from our bottom right all the way up. Well, now we're moving from our, for example, our top left, but we're moving to the right. So that's why we're affecting the ray vector is affected in the x component by how far along we are in the loop, because we're looping in the other direction effectively. Okay, let's go ahead and say debug.drawRay, so we can draw this ray out. We'll pass in ray vector, we'll pass in ray direction, and we'll multiply that by ray distance. And we'll color it red. Again, this will just visually show us our rays that we're casting so that we can know that our calculations are correct. Next up, we need to do the actual raycast. So we'll say raycast hit equals physics2d.raycast passing in our ray vector, our ray direction, our ray distance, and our platform mask. Remember, we only want to perform these raycasts against things that are in the platform mask. So that's because we don't want to be able to collide with things like a health bar, or a health pack or a star or something like that. Next up, we check to see if not raycast hit, continue. So that means if there wasn't a hit, if we cast the ray out and we didn't hit anything, then they're good to go. They don't need to do anything more. Okay, so next up, what we have to do is some interesting bit of logic. We need to keep track of what we're standing on. The reason we need to keep track of what we're standing on is when we go out to actually create our platform logic, we need to be aware of what platform we're standing on, so that we can move with the platform we're standing on. Hopefully that makes sense. So we need to know what we're standing on. So what I'm going to do is I'm going to write some code that actually affects the property that we haven't implemented yet. So I'm going to say if not is going up. What is not is going up? It means if we're going down, then the vertical distance to hit equals transform.position.y minus raycasthit.point.y. I almost started typing in pony for some reason. Then what I want to do is basically the logic for finding which platform we're standing on is effectively going to be what is the ray with the shortest distance to that object that we're casting. So what I'm going to do is I'm going to say if vertical distance to hit is smaller than standing on distance, then standing on distance equals vertical distance to hit, and then standing on equals raycast hit collider dot game object. Now note that standing on is a property that doesn't exist yet, but when it does exist, it's going to contain the platform that we're standing on. Okay, next up we have some standard stuff. We're going to say delta movement.y equals raycast hit dot point dot y minus ray vector dot y. Okay, so this code pretty much mirrors what we did with movement horizontally. We basically use this expression to determine the farthest distance we can move down or up without hitting anything or without hitting an obstacle. Sound good?
Yes, it does.
Awesome. So then let's go ahead and do another thing that we did before with our move horizontally. I'm going to say ray distance equals mathf abs on delta movement y. So again, since we're casting multiple rays down or multiple rays up, we only need to worry about casting another ray that is the furthest away from an object that we had previously hit. Then we're going to say if is going up. That means that we need to subtract the skin width from our delta movement.y, and we need to set state.is colliding above to true. That means we've hit a ceiling. Otherwise, delta movement.y is skin width is added to delta movement.y, and state.is colliding below is set to true. That means we're on the ground. Okay, we need to do two more things. One is specific to slopes. If we're not going up, meaning we're going down, and the delta movement.y is greater than 0.0001 f, then state.is moving upslope is true. Upslope, sorry. So if our delta movement is greater than a very small value and we're going down, that means we're moving up a slope. Finally, we have to do that small little sanity check. We need to make sure if ray distance is smaller than skin width plus a very small factor, 0.0001 f, then break out of the loop because we have nothing else that we want to do. All right, so that's our move vertically code. So now we can see that it's pretty much, I guess there's not even really a point to diagramming this out because it follows exactly what our move horizontally does. The only difference is that we keep track of what platform we're standing on, and we have some additional handling for slopes, which we'll talk about in a later video. Other than that, it's pretty much a mirror copy of move horizontally, except we're talking about the a different axis. So let's go ahead and create the standing on property, because we need the standing on property in order to track if we're standing on anything. So I'm going to scroll all the way to the top of the file. I'm going to find my properties, like right here. I'm going to say public game object standing on get private set. That'll make our code compile, because now we have a public property standing on that I can use to store which game object we are standing on, which again will be used in a later video when we talk about moving platforms. Sound good?
It does indeed. Let's go.
All right, so again, this is our move vertically method, and that should allow us to move vertically. Let's go ahead and exit out the full screen, come back into Unity, and see what kind of changes this makes to things. So if I hit play, watch what happens. I don't know if you guys saw that actually. Let's make this a little bit more obvious. I'm going to select my player in the scene view, and I'm going to move him into the world, right? Then I'm going to come back here in the game, and I'm going to watch. You see how he starts floating up? That's because the rays that are being cast within underneath his skin are returning a negative result for how far he can move in the Y direction. So they're actually pushing him up because of the skin width. So now we see that we do indeed handle horizontal movement, and we handle vertical movement to an extent. There are two more aspects to vertical movement that we need to take care of. One is going to be gravity, and the other one is going to be jumping. So those are the two new features that we can add to the game now that we have proper vertical movement. Let's work on gravity first. Let's have this character start all the way up here, and then hit play and see what happens. Well, it's not very interesting. He can move right, he can move left, but as you see, he doesn't fall down. That's because we haven't implemented any gravity yet. So let's go ahead and do that. Gravity is actually incredibly easy to do. All we have to do is go back into our character controller 2D, scroll all the way up to our late update method. Inside of our late update method, I simply have to do velocity.y plus equals parameters.gravity times time.delta time. So what are we doing? All gravity is a force that affects our velocity over time. That's really all gravity really is. So by doing this, we will force the player to go up or down based off the gravity. Yes, you could have a gravity parameter that makes the player go up instead of down, although that isn't really physically possible in the normal world. It might provide some interesting aspects to your game if you were to choose to do that. Let's come back into the game and hit play and see what happens. As you see, he does indeed, I don't know if you guys saw that, he does indeed fall to this platform, then he stops falling. If I move him over here, he falls to that platform and stops falling. Now remember, the gravity component is added through our character controller script through our default parameters, and we see that right now the gravity is set to -25. Alrighty, so that's gravity. That's vertical movement. That's gravity. Let's go ahead and talk about jumping. So jumping is going to be handled in a couple of different cases. First of all, I need to have some sort of concept of how much force needs to be added to a player when he decides to jump. So what I'm going to do is I'm going to come over here to my controller parameters 2D class, and I'm going to add a new parameter to it, or a new public field to it. I'm going to say public float jump magnitude. I'm going to set this to 12 by default. The jump magnitude is how much force is going to be added to his y component of his velocity if he does a jump. All right. So let's jump over to Character Controller 2D, and we can now implement our jump method. Well, we can implement most of it. So let's go ahead and say add force, because we're adding a force, and let's say new vector2. Let's go ahead and pass in 0 in the x. Now we'll come back to this later when we add moving platforms. So I am going to add a to-do in here, say to-do moving platform support. But the force that we're adding in the y direction is going to be parameters.jump magnitude. Now we want to do one more thing. We want to say jump in equals parameters.jump frequency. Jump in is used to determine if a player can jump or not. Remember, in certain cases on our parameters, we might want to limit the amount of times a person can jump in succession. In this case, it's set to 0.25, which is a quarter of a second. So if we jump back into the Character Controller 2D, we have the jump in set right there to the jump frequency of the parameters every time they jump. But how does jump in decrease? Well, what we're going to do is on late update, we're going to say jump in minus equals time delta time. Alrighty, so that pretty much is the code that we need on the Character Controller 2D for jumping, with the exception of actually adding the jump in parameter to our code, and we haven't implemented our can jump method yet. So let's implement our jump in field first. Let's scroll up to the top to our fields and say private float underscore jump in. That'll make that code work. So now our jump in is being set to something, but it's not being used. That's because we haven't implemented our can jump property yet. So go ahead and locate your can jump property, and we're going to write some code. So what I'm going to do is first of all, I'm going to break this out. I'm going to format this so we have some more room to work with our property. Then I'm going to say if parameters.jump restrictions equals can jump anywhere, then return jump in is smaller than 0. Otherwise, return state is grounded. All right, so what does this mean? Well, this means that we can jump if we have a jump restriction of can jump anywhere and our jump in is smaller than 0, or how about smaller and equal to 0, or equal to 0? Or if our jump restrictions are not can jump anywhere, that means they can only jump if he's grounded. As you can see, the only other option is, or can jump on ground. There's a third option, which is can't jump at all. So let's go ahead and fix that property real fast. I totally forgot about that enum member. I'm going to say if parameters dot jump restriction equals can jump on ground, return state dot is grounded. Otherwise, return false. And the reason why we're returning false is because the only other option of this enum is that he can't jump at all. All right, so come back to Unity, hit run. Let's see if we can jump. We can jump indeed. Can't jump very high. I think I'm going to go in here to my character controller and change my jump magnitude to maybe 20 instead and hit play. Maybe that's a little too high.
16.
I'm trying to get on one of these platforms, but because I implemented my character controller properly, it's kind of hard. Um, 16? Alright, let's try a jump magnitude of 16. I think that's pretty good.
That's a pretty hefty jump.
Now our character controller isn't perfect yet, but it's actually shaping up pretty good. As you can see, we have gravity implemented. We have collision both vertically and horizontally implemented. There might be a few cases where we run into issues that we'll see later. And then especially obviously our moving platforms are having a little bit of a problem. And we just fell. And we will continue to fall. You can even see that he's trying to cast rays to find a platform, but alas, it's not meant to be.
It's all gone.
Why is he casting rays up? We might have a bug. What I'm going to do is I'm going to go ahead and make my scene view and my game view appear. And I'm going to focus on my player. Okay, those are up and to the left. Up and to the left. Down.
Was it because he dropped into a negative Y?
No, it shouldn't be that.
Was he casting them down, but he was falling so fast that they looked like they were going up?
Maybe. It seems my rays are inside of him. But I think that, yeah, that's the skin width that we're looking at. I might need to tweak the skin width a little bit, I'm thinking. Anyway, I don't think that this should be a problem, but of course, if it ever becomes a problem, we can take a look at debugging that in the future. But for right now, everything is acting in the way that it should, given that we haven't yet implemented some of the functionality yet, particularly handling vertical and horizontal slopes, as well as handling moving platforms. So I think this should be good for what we're doing right now. Alrighty. In that case, we have jumping, we have gravity, we have vertical movement, we have vertical collision detection, and everything is good. So I think that just about wraps up this video. The next video, we're going to be looking at slopes.
All right.